Good morning, Droitwich. You can see we're getting serious this morning. The science of Santa. So no youngsters in the audience, so we're not going to send anybody home crying by the looks of it. Okay. The question I'm addressing this morning, because I am a scientist, is this one. Is Santa compatible with the laws of physics? Or if you want a slightly more pithy way of asking it, how many laws of physics does Santa actually break? If asked by a young niece or nephew, is Santa real? I thought, well, I don't want to lie to youngsters, so how can I answer that correctly and not disillusion them completely? So I had to think about this, and I thought, right, this is a suitable talk. It's only a short talk, you'll be glad to know. So in less than half an hour, we'll be done, and you can return to the mince pies if you so wish. So I'm sure we all know that Santa is, at least allegedly, a portly, jolly fellow with a white beard and a penchant for wearing red suits. Okay, fine, but just because he displays questionable fashion sense doesn't mean he can't exist. So the question is, what about the claims that are made by... Gosh, it sounds like it's absolutely chucking it down out there, doesn't it? Okay, what about the claims made regarding his incredible feats? So let's remind ourselves what it is that he's claimed to be able to do. So Santa allegedly visits all households on Christmas Eve and delivers presents to all qualifying children. How do children qualify? Well, it depends, of course, whether they're on the naughty or nice list. And the question is, can we reconcile that rather amazing statement with our understanding of the way the world works, the way the universe works? And in particular, I thought, well, maybe rather than start from scratch, what I can do is actually use the science that I've actually already been describing in various other outreach talks that I give. I've got about 40 to 50 sciencey talks. There's just a small selection of them. You've had one or two of those. And I thought, can I just borrow a few concepts from the science that I've delivered in those talks to actually address this particular question? Okay. So let's remind ourselves, there it is bigger. What is the statement that we're trying to address? The statement is that Santa visits households on Christmas Eve to deliver presents to children. And what we're going to do is scientifically, forensically, dismantle that particular statement and see if it actually stands up to scrutiny. First, let's remind ourselves how many children it is that he supposedly delivers presents to. Quite a few, presumably. Okay, the population of the Earth at the moment is about 8 billion people. Apparently, 1/4 of them are children. But if we're defining a child as under 18, does Santa deliver to 18-year-olds? Well, maybe, maybe not. And let's assume that 50% of those children are eligible for Christmas presents. Let's assume that Santa is relatively generous and agrees to deliver presents to children, even if they're not in Christian households. So you end up with something like 1 billion children are expecting presents at Christmas. And again, the asterisk there reminds us that, well, it depends on how many are on the naughty or nice list. Just to keep the numbers nice and round, let's assume that none of them are on the naughty list and everybody's on the nice list. Any parents or grandparents in the audience may question that particular ratio, but let's just assume it's valid just to keep the numbers nice and simple. 1 billion children. Okay, so that's the audience, as it were. Santa visits various households, not necessarily 1 billion households, depending on how the children are distributed around the world. But somehow he visits them all on Christmas Eve. What's his mode of transport? Well, we know his mode of transport is a sleigh, and of course the sleigh is pulled by flying reindeer. So, scientifically, we can ask the question, can reindeer fly? Well, we know that insects fly, and we know that birds fly, and we know that pterosaurs fly, though you don't see them so much these days, and we know that some mammals can fly. So the question remains, can reindeer fly? Well, if they can, they choose not to do so for a lot of the time, because most of people seeing reindeer and photographing reindeer and video reindeer seem to be all 4 hooves on the ground. But we have to remember that even if there's very little evidence for reindeer being able to fly, remember the scientific mantra, and that is, absence of evidence is not evidence of absence. They are two very different things. Just because we don't have photos of reindeer flying doesn't mean they can't. So we don't know. The answer, can reindeer fly? The jury is out on that one. We have neither proof nor disproof. So we just have to leave that one in the air, if you excuse the pun. Okay, so how fast would Santa have to go in order to achieve these feats? Well, to visit 1 billion children, we can sort of assume that they're spread over the world. Of course, they're probably concentrated in a lot of cities around the world, not strictly speaking uniformly spread, but we can still calculate, roughly speaking, Santa would have to travel at least 2,000 kilometers per second, which is quite fast. But as far as a physicist is concerned, quite slow, because it's only 0.007 times c, the speed of light. And remember, that's the only speed limit in physics. Going fast, going slow, there's only one speed limit, and that is the speed of light. I have a series of talks that I call Fiat Lux, that's Let There Be Light. And in Fiat Lux, I talk about the nature of light and actually measure the speed of light, and it turns out to be 300,000 kilometers per second. So Santa is only moving at somewhat less than 1% of the speed of light. He is nowhere even close to breaking that particular law of physics. So that's not a problem. So we know that nothing can travel faster than light through a vacuum. And bear in mind that, yes, when we look out into the universe, we see the universe is expanding, and actually space can expand faster than that. So some galaxies are indeed receding from us faster than the speed of light. But in terms of moving through space, the speed of light is the speed limit. But we're less than 1% of that speed limit, no problem whatsoever. Okay. But surely, if he's moving really fast through the atmosphere, wouldn't the sleigh heat up? Wouldn't we end up with roast reindeer? Because everything is going to get really, really hot. We know that when a meteor, small grain, about the size of a grain of sand perhaps, coming into the atmosphere, or a bigger rock like an asteroid, if it comes into the Earth's atmosphere moving at great speed, it's not friction that heats it up, it's the fact that when things move quickly through the Earth's atmosphere, they compress the air in front of them, and when you compress gases, they get hot. This is something I cover in what I call the ABC of stellar evolution. The C means compression produces heat. That's how stars are born. If you take a large cloud of gas and let gravity do its stuff, as the cloud of gas gets compressed, it heats up. And that is what ignites stars. And anybody, even if they're not stellar evolution physicists, know that when you pump up a bicycle tire, for instance, the pump and the tire and you get hot because you're compressing the air inside the tire, and compressing the air heats it up. So we know compression produces heat. Even if it's aerodynamic, even if the sleigh looked something like that, which is not how we normally portray it, even if it was a very sleek design, it would still compress the air in front of it if it's moving really fast. So if you know that compression produces heat, and generally speaking, hot objects radiate light. Any object we choose, whether it be a mince pie or a table or a laptop, if you take an object made of matter, if you heat it up enough, it will glow. You are glowing in the infrared because you're radiating, well, actually quite a bit at the moment. You're radiating at about 300 Kelvin. You're radiating infrared light. If you get things hotter, they start to radiate visible light. If you get them hotter still, they'll probably radiate some ultraviolet light as well. So if we know compression produces heat and we know hot things glow, then you should say, well, Santa zooming around all over the world should be visible as a very bright light in the sky. And you might say, oh, well, maybe it was. And I think it's pushing it a bit to say Santa's sleigh is actually responsible for the Star of Bethlehem, because I think we're getting the timeline slightly mixed up there. But you could say that if Santa's sleigh is visible all the time on Christmas Eve, then you could say, well, yeah, there's plenty of people who say that, yep, there are definitely lights in the sky. Not necessarily only on Christmas Eve, but certainly there are bright lights in the sky. So maybe Santa's sleigh is responsible for that. But actually, we know about matter in the universe which doesn't glow when it gets hot. Virtually everything around us, everything we know about, everything that sort of agrees with common sense, heated up, it glows. However, there is some material which doesn't emit light and doesn't absorb light and doesn't reflect light, and no matter how much you heat it up, would not glow and be visible. What type of matter is that? It's what we call dark matter. We know there's lots of it out there. It's embarrassing to say that physicists still don't understand what it actually is. But when we look at all of the matter in the universe, 85% of it is this stuff, dark matter. Only 15% of it is the stuff that's lying around in this room, like the mince pies and the tables and the laptop and you. So there's an awful lot of stuff out there which doesn't behave the same way as the matter we're used to. So if Santa and his sleigh and his reindeer were made of dark matter, then even if they got really, really hot, moving at speed, then they wouldn't glow. So maybe that's an explanation. There's another little aside, and that is, given that dark matter doesn't absorb light or emit light or reflect light, it also means that Santa's sleigh wouldn't show up on radar, because radar is just radio waves. They would just go straight through, they wouldn't reflect off, and you wouldn't get a ping. So when NORAD tells you, or your youngsters, that they've seen a radar ping from Santa's sleigh, they're lying. They're lying to children, basically. Santa's sleigh does not show up on radar. Okay. So what have we done? We've done children and we've done visits. So Santa visits households. Okay. How does he enter each household when he gets there? How does he get down the chimney? He would have to get down an awful lot of chimneys, something like 3,000 chimneys a second. That's pretty fast, especially when you consider that he's a portly fellow with a little bit of a girth, and most chimneys are only sort of, 10 or 20 centimeters or so in diameter, and therefore it would be a problem for him to get down. So how does Santa get down a chimney when the chimney is clearly a lot smaller than he is? Well, it can be done in principle. We know that, we assume that everything is made of atoms. Let's put dark matter to one side for the moment. If he was made of atoms like us, we're made of molecules. Molecules are made of atoms. Atoms comprise a nucleus and a whole load of electrons going around them. If you were to take an atom and keep the nucleus but replace all of the electrons with muons, muons are a sort of cousin of the electrons. They're very much like electrons. They're just 200 times heavier. They are another subatomic particle, a bit like an electron. Negatively charged, so they would make atoms just like electrons can be used in atoms. But the atom that you would make, if you replaced all the electrons with muons, the atoms would be 200 times smaller, which means instead of Santa being somewhere between 1.5 and 2 meters tall, he would be about a centimeter high. And he would fit down a chimney, no problem whatsoever. Muons are heavier than electrons, but most of the mass of an atom is in the nucleus anyway, so it wouldn't really make much difference to Santa's mass, but it would make a difference to his size. So he would fit down the chimney, no problem whatsoever. Yes, you might say, but what if there's no chimney? A lot of houses these days are built without chimneys, and of course we're also talking about flats or apartments, etc., which don't have a chimney. So how does Santa get inside these households if there's no chimney to come down? Well, just like we can use the idea of our knowledge of quantum theory and how atoms are put together to say, in principle, he can make himself smaller just by replacing electrons with muons. I don't know quite how he would do that, but in principle he could. There's another option for how you get inside without going down a chimney. Quantum theory, again, tells us how things behave, especially on the very small scale. Quantum theory says it is perfectly possible to get an object from A to B, even though there's an impenetrable barrier between them. Even though Isaac Newton would say that is impossible, according to quantum theory, it can happen. And we see it happen. And we have built devices that use this particular property, that you can go from A to B, despite the fact that there's a barrier between them. The process is called tunneling, or quantum tunneling if you prefer. Tunneling refers to the fact that you can go through a wall rather than having to go round the wall or through an open window or through an open door. So in principle, Santa could tunnel from the outside of a domicile to the inside without ever passing through an open door or an open window. We know that that is possible because we've seen it happen and we've built microscopes based on that principle. So we don't normally see it happening on the large scale, but maybe Santa has figured out a way of getting the quantum world to basically dictate the way he behaves. So again, he's not breaking any laws according to our understanding. So we've looked at children, visiting, households. What about the fact that he does all this on Christmas Eve? Christmas Eve doesn't mean just the night. Remember, if you use the time zones of the Earth appropriately and you go round in time zone order, you actually have something akin to 36 hours to play with. So although it's in principle all on one night, actually we're saying all in a 36-hour period. So how can everything be done in a 36-hour period? Well, there's no reason why, in principle, Santa can't be in two places at once. Again, we're relying on quantum theory, and we know that if Santa is made of molecules, and molecules are made of atoms, and atoms are made of subatomic particles, all of these things we know when we study them, we know that they behave in a rather non-common sense way. If quantum theory is ever at odds with common sense is wrong, and quantum theory is right. We have, in 100 years of quantum theory, we have never found it to actually give an incorrect prediction. It often goes against common sense, so we have to put common sense to one side. It is possible for objects to be in two places at one time. That doesn't seem right. You would say, well, either this laser pointer is in my right hand or it's in my left hand. It can't be in both at the same time if my hands are separated at two different points in space. But according to quantum theory, yes, it can. An object can be in two states at once. An object, for instance, can spin clockwise and anti-clockwise at the same time. We've never seen the Earth do that. The Earth spins one way and keeps spinning one way, apparently. But when we look at quantum theory, it tells us that, yes, you can spin both ways at the same time. You can be in two different positions at the same time. And there's actually no limit to why it's only two. In principle, an atom or a molecule can be in three places at once, or 5, or 10, or 1,000,000, or 1,000,000,000. There's no limit in quantum theory as to how many different places you could be at the same time. So again, maybe Santa has figured out a way of using this to his advantage, and maybe Santa can be in 1,000,000,000 places at once. Okay, again, I don't know quite how he's managed that, but it doesn't break any laws of physics. Well, if you don't like that and say, poppycock, he can't be in more places than one at a time, okay, let's put that to one side and say maybe there's an alternative way that he operates. And that is, he might be capable of manipulating space and time. Now we're not talking about looking at the micro world of quantum theory, we're looking at the macroscopic world. When we look out into space, we realize, according to, for instance, Einstein's way of looking at the universe, general theory of relativity, it looks like matter distorts space. It can warp space and it can warp time. We generally only see this in extreme cases when we're looking at very massive, very compact objects like stars or black holes. But we know in principle that even the Earth and the Sun distort the space around them. In principle, all matter will distort space. So maybe Santa has figured out, again, a way of using this to his advantage. Maybe he's figured out that instead of going to visit 1 billion different places, maybe he can simply distort space and compress space to bring all of those domiciles to him, rather than have him visit all of these things. It's a bit like the idea of how the Starship Enterprise gets from A to B. It doesn't go at incredible speed. It distorts the space ahead of it to bring the stars to the spaceship. Okay, so maybe Santa does the same sort of thing. No reason why not. As far as we understand, that is perfectly possible, according to our understanding of space and time and matter and gravity. Okay, Santa visits households on Christmas Eve we're up to delivering presents to children. Okay, so he's got to do all of these things whilst carrying presents for 1 billion children. Okay, yeah, how's he going to do that? Santa's sack. How could Santa carry all of these presents? How could he carry that many? If we assume one present per child, that's about all we can go with. Let's not assume that we've got dozens and dozens per child. So 1 billion presents. The sleigh isn't that big, presumably. It's being pulled by 8 reindeer. So the sleigh is a few meters in size, so you can work out the volume of the sleigh. If it's a few meters long and a few meters wide and a few meters high, you can work out the volume. But bear in mind, for any given object, the volume inside is not necessarily the same as the volume outside. Some things are bigger on the inside than they are on the outside. And if you're thinking Doctor Who's TARDIS, and if you're thinking that's science fiction, wrong. This is science fact. We know, or at least we know in the sense that it fits everything we understand about the way the universe works. For instance, black holes are bigger on the inside than they are on the outside. Now, if that is true of black holes, maybe it's true of other things. It's again a consequence of the fact that matter distorts space. And the idea of the volume inside something with a given surface area, well, that depends on the geometry of space. As soon as we start distorting and warping space, then you can't assume the volume on the inside is simply the same as the volume you would calculate from the outside of any given object. So, although we think of it in terms of an astrophysical phenomena, again, maybe Santa has figured out how to make the sleigh bigger on the inside than the outside. In which case, maybe it's so big on the inside, he's got enough room for 1 billion presents. That might be the case, but if you don't like that, again, there's an alternative. We believe there are 3 dimensions of space, or at least there are 3 dimensions of space that we can perceive: forward, backward, left, right, up, down. But many scientists believe there's actually more than 3 dimensions of space. And for some reason, we simply have difficulty perceiving those extra dimensions. Some people believe there aren't simply a few more than 3. There could be 10, 11, 12, possibly more, depending on if you're a mathematician or if you're a physicist. The fact that we don't know where those other dimensions are, and we can't draw them in a 3-dimensional picture, and we certainly can't draw them on a 2-dimensional diagram, just because we can't visualize them doesn't mean they're not actually there. So maybe those extra dimensions do exist, and Santa has figured out a way of accessing them. So all you need to do is to take your 1 billion presents, shift them into this extra dimension, in which case they would appear to disappear from our 3 dimensions because they're no longer in our 3. They've been moved into the 4th, 5th, 6th, 7th, 8th, 9th dimension. They would appear to disappear. Santa then goes visiting these various households, and then when he's there, he pulls them out of this extra dimension, puts them under the tree. Okay, so again, not actually breaking any physics. It's a question of stretching the definition of how many dimensions are there, but the basic answer is we don't know. So he's not necessarily breaking any laws, especially when we don't know how many there are, and there could be a lot more than just the 3 dimensions that we all perceive. Okay, I've said various things are possible, and you might now be possibly a little bit incredulous, saying, well, yeah, okay, they might not be impossible, but surely they would need an absolutely huge amount of energy to do any of these things that we're talking about. Santa and a sleigh and 1 billion presents, moving at huge speeds across the world, distorting space and time and invoking the energy required to change the way atoms are put together. Surely that would require ridiculous amounts of energy. Yes, it would. But Santa does have access to ridiculous amounts of energy. How so? Well, for instance, if he decided to power his sleigh with a black hole can produce an enormous amount of energy. How big would the black hole have to be to power his sleigh? Something the size of a grain of sand would be more than big enough to power the phenomena that we've been talking about this morning. It's enough to power a starship and send us to the stars, so it's certainly enough for a sleigh. But there is something else. There's another energy source other than something weird and wonderful like black holes. There's an energy source that we've been overlooking. It's the elephant in the room. What happens to all the mince pies? if households leave mince pies for Santa, I mean, nobody thinks he actually eats them all, surely. Come on, let's be reasonable about this. Let's be serious for a moment. He doesn't actually eat that many mince pies. What if Santa could convert all the mince pies directly into energy? We know the conversion rate from mass to energy. Einstein tells us E equals mc squared. So we can work out what the energy content, the energy equivalent, if you like, of a mince pie is. And then we can do some sums to work out how much energy does Santa have available to him over the course of the night. So let's do that. If you really don't like maths, well, what are you doing in this group if you don't like maths? But okay, let's do it anyway. 1 mince pie equals mc squared. A mass of a mince pie is about 50 grams or so, taking a standard pack of 6. So a 50-gram mince pie multiplied by the speed of light squared in standard SI units, you get an energy of 5 times 10 to the power 15 joules. We'll come back to joules. It's the favorite energy of a physicist. Other people might think more in terms of calories rather than joules, but that will do for the moment. How many mince pies would be left? Let's assume that not everybody leaves mince pies. Let's assume just a few % of households leave mince pies. Perhaps the households with particularly young children, maybe. A few % of households leave a mince pie for Santa, so let's just round that up and say, let's assume it's 20 million out of the billion households or so we're talking about. 20 million mince pies, so we take 20 million multiplied by that number for each mince pie. We get a total of 10 to the power 23 joules is the total energy content of the mince pies left out for Santa. And the question is, well, what's that in a number that makes sense to me? Okay, how big is 10 to the 23 joules? Imagine the power output from a nuclear power station. A nuclear power station generates something like a gigawatt of power. That means a gigajoule, 1 billion joules every second. Imagine the energy output from a nuclear power station running second by second by second, every second of the day, every day of the year, for 1 million years. That is 10 to the 23 joules, roughly, give or take a factor of 2 or so. So, if Santa can take the mince pies and convert them into energy, he doesn't need to worry about the carrots and the brandy, that's all he needs, the mince pies. If he can convert the mince pies mass into energy, he has access to 10 to the power 23 joules. Overnight, he has the energy equivalent of a nuclear power station running for 1 million years. More than enough energy to do all the things I've been suggesting this morning. Okay, next question. How do you get the energy out of a mince pie? How do you extract E equals mc squared from a mince pie? Well, there's at least 2 ways I know of doing this. The most efficient way of extracting energy from matter is to take the matter, in this case a mince pie, and then you take an anti-mince pie and you collide them together in the Large Mince Pie Collider at CERN. That will deliver all of the energy. That basically is what you do with protons and antiprotons. Collide them together, all of the energy comes out. But the problem, I'm sure you can guess, is where do you get all the anti-mince pies from? Antimatter mince pies are not very common. Nobody leaves them out for Santa. So although in principle this is a very efficient way of getting energy out of matter, it doesn't work for Santa because of that problem with the antimatter version of the mince pies. So we have to find a different way of extracting energy from mince pies. We know of a mechanism which is reasonably efficient. It's not 100% efficient. You won't get 100% of the energy out of matter, but you can get 5% or 10% or 20% or 30% of the energy out of matter, even without antimatter. What you do is you take the matter and you drop it into a black hole. You can see black holes are a common theme in this particular morning's talk. If you take matter and drop it into a black hole, an enormous amount of energy is released via mechanisms that I'm not going to talk about in detail. But we know it happens, even though we can't test it in the laboratory. We know it happens because there's lots of black holes out there, and we can watch it happen for these black holes. Quasars are a type of galaxy with a very active nucleus. A huge amount of energy is pouring out of the nucleus of these galaxies which become labeled quasars. What's going on there is that there is a supermassive black hole at the core of this galaxy, and matter is falling into this supermassive black hole. The matter is probably not mince pies, admittedly. The matter is probably gas and stars falling into the black hole. But the point is, as this matter falls into the black hole, it's effectively ripped apart, and before the matter gets sucked into the black hole itself, a huge amount of that matter is converted into energy and radiated away as light or ultraviolet or X-rays, all part of the electromagnetic spectrum. We know it happens, and these quasars are very bright. During COVID, back in 2020, perhaps you can't read that, a little talk I give, back in 2020, I asked myself, can I actually image one of these very distant galaxies? And even without using a telescope, just using my Nikon camera, I photographed one of these quasars. This quasar was 25 billion light years away. That's on the other side of the observable universe. But it's possible to pick up its light, even without a telescope, because so much energy is coming out of these quasars. And the only production of this amount of energy, we believe, is matter falling into a black hole. So if it gives us that much energy that we can see an object on the other side of the observable universe, then I'm pretty sure dropping mince pies into a black hole will give us an enormous amount of energy as well. I'm not too sure exactly how much, because no matter how much I looked, I couldn't find any numbers on this. Nobody seems to be researching this. Nobody is studying how much matter falling into a black hole will give you how much energy if the matter happens to be mince pies. Plenty of people are doing these calculations for stars, duh, but mince pies, no, nobody seems to be working on that. So I haven't done the back of an envelope calculation myself, but I'm pretty sure if it works for quasars, it works on a local scale for Santa. So with that number of mince pies, he has more than enough energy to play with. Okay, maybe he's not breaking any laws of physics, because these things are technically possible. They're possible if you have enough energy, and it looks like, depending on how he acquires that energy, he's got enough energy to play with. But you can still ask the question, even if this is possible, how does Santa know how to manipulate quantum mechanics and use it to his advantage? How does he know how to warp space and time? How does he effectively get a tame black hole to power his sleigh, for instance? Well, one thing to bear in mind is at no point have we actually said that Santa has to be human. Remember that kids are asleep when he arrives, so they don't actually see Santa. And therefore, we don't really know what he looks like. So maybe he has a few skills that we're not too familiar with. But again, just because we don't know how he does it, doesn't mean he can't. So coming back to the original question, is he compatible with the laws of physics? Or how many laws of physics does Santa actually break? I would argue the answer is, well, none. So you can draw your own conclusions about the existence or otherwise of the portly, jolly fellow with a white beard and the penchant for wearing red suits. And regardless of the conclusion you come to, well, may I wish you all a very Merry Christmas.